And welcome back. We're going to go over question number 1 from 2016. This was a quiz, so if you haven't done it yet, please do not continue in this video. Make sure you do it first, and then come back and watch it and grade and see how you did. So let's go ahead and get started with number 1 from 2016. It says water is pumped into a tank at a rate modeled by W of T in liters per hour over the interval 0 to 8, where T is measured in hours. Water is removed from the tank at a rate modeled by R in liters per hour, where R is differentiable and decreasing over that same interval. Select values of R are shown in the table above. At time t equals 0, there are 50,000 liters of water in the tank. So what I want to note here is actually this kind of problem could have been classified as a rate in, rate out problem, and we're going to do more of those examples later on. But for now, we want to make sure that we understand the context and the understanding of what these functions represent. So W, it says, is the rate at which water is being pumped into a tank. So we would say that this is the rate in, and then it says that R is the function that represents the water, how the water is being removed from the tank at that rate. So R is a rate out. So we have the rate in represented by W and the rate out represented by R, and both of those have units of liters per hour. So understanding those units is going to help us understand what we're going to do with these functions when we come across these questions. So in part A it says estimate R prime of 2. Well, we're given values of R and we're asked to estimate R prime. So we're asked to take the derivative of R, but we can't because we only have a table of values. So to estimate R prime of 2, we're just going to take the slope over the interval 1 to 3. So we end up with R prime of 2 is approximately 950 minus 1,190 all over 3 minus 1. We can simplify that a little bit to say negative 120. And then it says indicate units of measure. Because we're trying to find the derivative of R, and R is measured in liters per hour, the derivative would be liters per hour squared. Now, a couple things to note. It says that this is an approximation, right? It says estimate, and we are estimating, so you want to make sure you have your little squiggly lines here, not exactly equal to. And then again with the units, it's liters per hour squared because we're taking the derivative of liters per hour. So technically, it would be liters per hour. So it's kind of like an acceleration in a sense. As far as points go, you're going to get 1 point for your estimate and 1 point for the correct unit. So it's absolutely important that you make sure you're paying attention to what it's saying here and answering the question thoroughly, because if you forget the units, that's a huge missed point, and it's an easy point to get on top of it. All right, part B, it says use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. So we are looking for the amount of water removed from the tank. So we're going to be using the function W because that is the rate out. That's water's being, we're going to be using R of T because that's the rate out. It says water is removed from the tank at that rate. And because we're looking for the amount of water removed, we're going to be taking the integral of R of T dt. And so thinking through understanding the units on this, the units on R of T are liters per hour, and then we're multiplying that by the change in T. So we're multiplying it by hours. So it's liters per hour times hours, which gives us a unit of liters, and that's exactly what we want here. We want to know how many liters have been pumped out. Because we're only focusing on the out part, we don't need to consider W, because that is dealing with the amount that's being pumped in. So anyways, the integral from 0 to 8 of R of T dt, we're doing a left Riemann sum using the 4 subintervals to estimate this. So we're going to say approximately. The width of the first one is 1, so 1 times. The left Riemann sum would be 1340, and then plus the width of the second subinterval, which is 2, and then times the left-hand value there is 1190, plus the width of the third one, which is 3, because the distance from 3 to 6 is 3, and then times the left-hand value, which is 950, and then plus the width of the last one, which is 2, times the left-hand value, which is 740. And then we can simplify that to 8,050, and the units on that would be liters. So we have there we have estimated the amount of water that was removed over that 8 hours. The next part of this question, it says, is this an overestimate or an underestimate? Remember, this deals with whether the function is increasing or decreasing, because we're talking about a left or right Riemann sum. So since this function is, what does it say? It says this function is decreasing, then we know a left Riemann sum will be an overestimate. So since r is decreasing, the integral, or the left Riemann sum, will be an overestimate. And again, if you need to draw a picture of that to see, to kind of visualize that, since we have a decreasing function and we're doing a left Riemann sum, that means we're picking the values from the left and moving to the right, we can see that those rectangles are going to be bigger in terms of area in comparison to the area under the curve. And so that's where that comes from. All right, as far as points go, you're going to get 1 point for the left-hand Riemann sum. So basically 1 point, let's see, 1 point for this line right here. Okay, so 1 point for this. 1 point for your approximation. So 1 point for having this answer here. And then 1 point for saying that it's an overestimate with your justification that the function is decreasing on a left Riemann sum. Again, emphasizing this point, you do not have to simplify any further than this expression. This is all numeric and algebra or arithmetic from here, so you don't need to simplify that. So I would recommend not to. That way you don't make an arithmetic mistake. You would still get full credit. You would get the points for the Riemann sum and the approximation if you just leave it here. All right, so for part C, it says use your answer in part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. And so we need to think through this logically here. How do we know how much water is in the tank? Well, there's 3 things we need to know. We need to know how much water we started with in the tank. We need to know how much water was put into the tank. And then we need to know how much water is being taken out of the tank. Well, we know how much water was in the tank at the beginning. It says that there was 50,000 liters of water in the tank when t equals 0. So we can say, okay, we start with 50,000. From there, we need to add how much water was pumped into the tank. And so W of t represents the rate at which water is being pumped in. So to figure out how much water is being pumped in, we're going to take the integral of W of t dt, and it's going to be over the entire span 0 to 8. And part of the reason that is true is because we need this lower bound's time to match the initial conditions time. So we're going from 0 to 8. So this is how much water we started with. This is how much water was added. And then we need to subtract from that the amount of water that was taken away. Well, because R is the rate at which water was taken out, the integral of R will be the amount of water that was taken out. And so we can figure these values out. This is a calculator problem. So we can use our calculator to figure out the integral of W there. And so we'd end up with the integral of W would be 7,836.195. And then we already figured out the integral of R from 0 to 8 in the previous problem, and that was 8,050. And so we can just put all this together and we end up with 49,786 liters. Again, this is the amount that we started with. This is the amount of water that was added. This is the amount of water that was taken away. Understanding that the integral of the rate is going to give you an amount. The integral of this rate is going to give you the amount. And so that gives us the total amount of water that is in the tank at the end. As far as points go for this guy, you're going to get 1 point for having the correct integral expressions here. So if you had the integral from 0 to 8 of W of t dt and the integral of 0 to 8 of R of t dt, you would get that 1 point. You're going to get 1 point for the correct estimate, so 1 point for this guy here. And then, couple things to note. this is still an approximation. Even though the 50,000 is exact, and even though the 7,836 is exact, the 8,050 was an approximation, so this is still an approximation here. If you were to combine these integral expressions to say the integral of from 0 to 8 of w of t minus r of t dt, that would be fine. That's perfectly acceptable. But we wanted to separate them so we can look at these values separately because we already had this value. All right, anyways, part D, it says, for the interval 0 to 8, is there a time when the rate at which the water is pumped into the tank is the same as the rate at which the water is removed from the tank? So this type of problem is actually, at first you look at it and go, that seems pretty easy. That idea is pretty simple to understand. But once you dive deeper into what it's actually asking for, it takes a lot. This is a pretty in-depth problem. So the first thing I want to say is that we are looking for when the rate at which the water is pumped into the tank is the same as the rate at which it's removed. So remember, these functions, w of t and r of t, represents the rate of each of those. So we are basically looking for when w of t equals r of t. That's what we're trying to figure out. We're trying to figure out if there's a place where this is true. Now, the difficult part of this is that we could easily see it if we had two given functions, like we know w of t, but we don't know the function of r of t. We only know specific values of r of t. So that's where it gets kind of weird. But I do want to point this out. Because of the wording here, it gives us a clue. It says, is there a time when? That wording implies that we're probably going to be using one of our theorems, our intermediate value theorem, mean value theorem, extreme value theorem. Well, because it's asking about the rates being equal, and we are given information about the rates, that's going to imply that it's going to be the intermediate value theorem. And so the next step I'm going to do here is I'm going to actually subtract r of t from both sides, and you'll see why in a second. So we end up with w of t minus r of t equals 0. So if the question is asking, is there a time when the two rates are equal, that's equivalent to saying, is there a time when the rate in minus the rate out equals 0? And so now we have a function here that we're trying to figure out whether this function is equal to 0 at any point. So what I'm going to do is I'm going to notice this. I know that w of 0 is 2,000. How did I know that? Well, I just plugged in 0 to t here. And when I plug in 0, I get e to the 0, which is 1, and then times 2,000. So I know w of 0 is 2,000. I know r of 0 is 1340, okay, because that's given in the equation. And therefore, 2,000 minus 1340 is going to be a positive number. It's greater than 0, okay? Then from here, I'm going to look at the end of my interval at t equals 8. Well, w of 8, when I plug 8 into t here and use my calculator, I end up with negative 81.524. And then r of 8 is 700. So when I subtract those two, I would end up with 81 minus 700, which is a negative value. So here we have a time when this function is greater than 0, and then we have another time for which the function is less than 0. So let me kind of draw this for you so you can see what I'm talking about. If this graph is representing w minus r, and we know that w of 0 minus r of 0 is positive, so we know it's somewhere up here, and we know at t equals 8, w minus r is a negative value, okay? So we have these 2 points. If these two functions are continuous, and we know that they are, we know that they're continuous based on the form of w, it's exponential, so that's a continuous function. And then it says that r is differentiable, which implies that r is continuous, so therefore w minus r is going to be continuous also. So this function is a continuous function. So we have to connect these two dots here with a continuous function. So it could go up and then down and then back up, or it could go straight across, or it could go down and then over. It doesn't matter how we connect them as long as it's a continuous function. Well, what do we notice in all of these cases? In all of these cases, that function has to pass through 0. If the function was above 0 at one time and is now below 0, we can say it must have hit 0 at some point by the intermediate value theorem. And so let's go ahead and write the justification for all of that here. We would say, since w and r are both continuous functions, we can say that w minus r is also continuous, which implies that the intermediate value theorem will apply, because the intermediate value theorem requires a continuous function. Well, since w of 8 minus r of 8 is less than 0, and w of 0 minus r of 0 is greater than 0, we can say that there is a time t such that w minus r must equal 0. And then as a result of that, since this statement is true, we can add r to both sides, and therefore we can say that w of t equals r of t, and therefore there is a time when the two rates are equal to each other. As far as points go for this guy, it's 1 point. You get 1 point, sorry, it's actually 2 points, I apologize. You get 1 point for talking about or translating the idea of w of t equals r of t into w of t minus r of t equals 0. And then you're going to get 1 point for your answer, and with your justification, that includes the intermediate value theorem. So this was a big, big problem and a lot of wording in order to get 2 points. So I didn't necessarily expect you to be perfect on this, but hopefully you follow the logic. Anyways, that wraps up this question. Please make sure you grade yourself on this question and the prior question and input your answers into Socrative. So those were 2017 number 1 and 2016 number 1. You're going to input your scores into Socrative. The next one you're going to do is a you-do problem, and that's going to be 2019 number 2. That is a calculator-based problem, so do this on your own, set a timer for 10 minutes, and then come back and watch the video and grade yourself to see how you did.